SwayamPrabha. Digital India. Educated India.
And the first measure that we are going to talk about is Goldfield quant test for detecting heteroscedasticity. And before we discuss about different tests, one thing you have to keep in mind, in presence of heteroscedasticity, in presence of heteroscedasticity, what we assume actually, the sigma square I is actually a function of x, Instead of being constant, it is a function of x, either increasing or decreasing, I do not know, but it is a function of x. Now, what type of specific functional form you will assume, depending on that, there is a separate test that the econometrician they have developed to detect heteroscedasticity. For example, let us say that I have assumed this type of functional form, sigma square into xi square. This is a specific type of functional form I have assumed between sigma square I and x. So, sigma square a constant factor multiplied by xi square. So, as x increases, you can understand how the sigma square I will behave. Let us say that this is our assumption about this functional form, and if this is the assumption, then the test, corresponding test actually is called Goldfield quant test, that Goldfield and quant they develop. So, this is called Goldfield quant test. Goldfield quant test. So, they have given different step for this Goldfield and quant test. What they say, if you have your observation on y and x, let us say this is your observation, this is my observation. So, the first step they say that arrange the x value from small to big. What is the first step? Arrange the x values from small to big. This is the first. Okay, small to big you have to arrange. Then what is step 2? In step 2, what they say, after rearranging the x from small to big, you delete C number of central observations. T number of central observation, C number, and this C equals to 4 when n equals to 40. Okay, n equals to 40, and C equals to let not 40, let this is 30, and C equals to 8 when n equals to 60, something like that. Okay, something like that. This is a rule of thumb. Basically, you delete C number of observation. Then in step 3, what you do, run 2 separate regression one for the sample consisting of small x values or smaller x i's and the other with higher x values. So, that means once you arrange the sample from small to big and then you delete C number of central observation, you will get 2 different samples. In one sample you will have small x values and in the other sample you will have higher x values, and collect RSS 1 and RSS 2. This is from the small x from higher x. Okay. If you have 2 sample, if you run 2 separate regression, you will get 2 different RSS. Now, what would be the degrees of freedom for RSS 1 and RSS 2? What would be the degrees of freedom for RSS 1? Can you think of? I have total n number of observation. I have deleted C number of observations. So, what would be the degrees of freedom for RSS 1 and RSS 2? It is very simple. If you have n number of observation and you deleted C, that means now you have n minus C by 2 for the first sample, and second sample will also have n minus C by 2, and then degrees of freedom would be n minus k, that means here it is n minus C by 2 minus k. So, that means this would become n minus C minus 2k divided by 2. This is also n minus C minus 2k divided by 2. Okay. This is the degrees of freedom for the RSS 1 and RSS 2. And now, if you construct a test statistic in this way, RSS 2 by RSS 1 and their corresponding degrees of freedom, then that basically will follow an F statistic with degrees of freedom n minus C minus 2k by 2 for the numerator and n minus C minus 2k by 2 for the denominator. So, this would become your F statistic, and if that calculated F statistic is greater than the tabulated F statistic at a specific level of significance, then what you will get, you will say that if calculated F calculated is greater than f tabulated, then we will say that reject H naught. And what is our H naught here? The H naught is no heteroscedasticity. No heteroscedasticity. Okay, that is the decision that you can take. Now what we will do? We will take one data set and then we will estimate a model, and after that we will try to detect the heteroscedasticity. And this is the data set. If you look at, we have a data on income and consumption. For how many observations we have? We have total 30 observations. And if n equals to 30, then you can understand we will remove, first we will estimate the model and we will get some initial impression using the graphical measure, right, using the graphical measure. So, here what you are doing, you are estimating this model. What is the model? Reg consumption, which is actually a function of income. Okay. Now, look at the result. As usual, the income is highly significant at what 1% level, because t statistics is 12.29 and corresponding p value is 0.000. Okay, 0.000. Now, if you try to put your error ui hat square along with your yi hat, then there is a specific command in Stata, and that will tell you, this command is basically RVF PLOT. This is the command. This is the command. Look at this. So, from this, what we can say, that though it is not very clear, the command is RVF plot, and what is the meaning? R for residual and then V for versus, residual versus fitted, F for fitted value of y. That is why the name RVF, residual versus fitted plot. In the y axis I have residuals, in the x axis I have I have fitted. So, this is basically, that means ui hat square and the fitted. That is how you are getting RVF plot. And then from this plotting, what you can observe, actually look at this. So, there is no clear pattern, but we can say that it is not constant. See, this is 0 line. I can say that there is some kind of increase in the error variance, some kind of increase, though it is not very clear. Okay, though it is not very clear, right? If you put another comma, let us say RVF plot, y line 0, then you will see this is a 0 line, and this is how your errors are behaving, right? It is not constant, okay? Some kind of initial impression, but it is not very clear. That is why what we need to do, we need to go for Goldfield and Quant test, right? Goldfield and Quant test. And what is the first step? You need to arrange the x data from small to big, and then it is not only about arranging the x, you have to match those values with y also for running regression. So, you cannot simply arrange the x data and then run, because you have to have that mapping between y and x. That is very time consuming, but in Stata there is a specific command, and if you put that command, then Stata will make your life very simple. How will you do that? You put this comma, sort x, and here it is sort x means income. Sort income, right. So, I will first sort income, and then what I will do, that I will first run a regression for the first total number of observation is 30, and I remove 4 observations, central 4 observations, and then that means the first sample consists of 13 observation and second sample consists of 13 observation. So, that means first I have to run a regression reg consumption income for the first 13 observation, and if you recall once again, how will you put that command? The command is in 1 by 13, that means from 1 to 13, 1 to 13. This is your first regression, right. This is your first regression, and then for the second regression, reg consumption, then income in. So, up to 13, after that 16, 14, 15, 16 and 17, these central 4 observations are deleted. So, in second regression you have to start from 18 to 30, okay, 18 to 30. So, this is how you have constructed. Now, what you should do? You should actually construct your F statistic, right, and how will you do that? So, that means you have to remember your RSS2 and RSS1. So, RSS2 is 1536.79. So, I will put on Excel sheet 1536. So, this is what is the value? 1536.79, that is RSS2, 1536.79, and then what is RSS1? RSS1 is 377.16. 377.16. If you divide this by this is your F statistic. So, basically what you have to do, RSS2 by RSS1, which is 4.79, okay, 4.79. And what is the degrees of freedom for the numerator and denominator for this? The degrees of freedom would be 11 and 11. So, that means while calculating, I will go back to our formula. This is our formula, RSS2 by RSS1, and here what you are doing, basically this if you apply this, I am not dividing by degrees of freedom because that is 11 and 11, and this is 4.07, 4.07. Look at once again how much I have calculated, 4.07, that is the calculated value, okay, that is the calculated value. And now what you have to do, you have to find out this is F calculated, equals to 4.07. You have to now find out F tabulated at 1% and 5% level of significance with 11 and 11 degrees of freedom, 11 and 11 degrees of freedom. If you do so, if you go to your F table and mention your statistic, F statistic, and then you will see that this is 2.82 at 5% and 4.46 at 1%. So, that means at least you can say that you can reject your null hypothesis at 5% level of significance. You can reject your null hypothesis at 5% reject null level of significance. So, reject H naught at 5% significance. But if you determine that no, I will reject the null only at 1%, then actually you cannot reject your null. That is why from the graphical representation also it was not a very clear indication about heteroscedasticity, but somehow you have some kind of indication because rejecting null at 5% is also sometimes acceptable. So, this would be your decision making. This is about your Goldfield and quant test. But one thing is not clear, why we are deleting the central observations. Why we are deleting the central observations? Because we want to see we have arranged the data and then we have deleted the 4 observations so that the residual RSS of the second sample becomes quite different from RSS of the first sample. Based on that logic only, we are deleting the central observations. Are you getting my point? First you have arranged the data from small to big, and then we are deleting the central observations also, so that my RSS 2 becomes significantly different from RSS 1. Higher the difference between RSS 2 and RSS 1, higher would be the probability of getting evidence for heteroscedasticity, because what we assume that error variance is not constant, rather it is increasing as x increases. That is why when I arrange and run the regression for the other sample, sample 2, where all the large x values are there, we assume that RSS 2 would be quite large than the RSS 1, and to make the difference to get a very stark difference between RSS 2 and RSS 1, the central observations are deleted. Okay? But there are certain limitations about this Goldfield quant test. First of all, the C, how many number of observations I will delete, there is no clear cut statistical rule which will say this is the value corresponding to this particular n. This is kind of rule of thumb. C equals to 4 when n equals to 30, C equals to 8 when n equals to 60, C equals to 10 when n equals to 120, something like that. Okay? But there is no clear cut mechanism by which I can detect the value of C. Okay? Value of C. So, that means limitations. What are the limitations? Limitations of Goldfield Goldfield quant test. Goldfield quant test. First is that there is no clear rule for detecting C. Secondly, if there are more number of explanatory variable, then the same procedure needs to be repeated. Here I have only one variable, one explanatory variable x, that is why it is very simple. I arrange x, delete the central C observations and run two different regression. But suppose I have now x1, x2, x3, x5 and x6. So, I have to arrange all these x variables x1, x2, x3, x4, x6, delete central observations and run separate regression. So, the process would be very time consuming. These are the limitations. So, in our next class what we will do, we will discuss about another test which is more general in nature. You do not need to delete these observations, that means at one go we can implement the test without repeating the procedure. So, we will go for more advanced test for detecting heteroscedasticity in our next class. Okay.